Alright guys, so we're grading our 3 through 6 right here. Let's start with the graph. Okay. The question is, where does f of x have a horizontal tangent line? Given that this is the derivative, f of x is a horizontal tangent line where the derivative is equal to 0, thus making the slope of a horizontal tangent line equal 0. So there's at -7, -1, 4, and 8. The derivative is equal to 0. But this one doesn't ask us to JYA, so we're going to give this one out of 3. We'll just do out of 2. Out of 2. Okay. So hopefully you found all 4. You can just basically, if you got 2 of them, 2 out of 4 you get 1 point. If you get 4 out of 4 you get 2 points. Okay, next, f of x has a relative max at those. Okay, we're trying to find relative maxima, which is where the derivative changes from positive to negative. So here the derivative is positive. Here the derivative is positive. So it changes from positive to negative here and here. Okay, so you get 2 points for each of these, and you get a point for the JYA. The JYA has to include some statement about the derivative changing from positive to negative. Okay, and you have to either say the derivative or use f prime of x. You can't just say the graph. Okay, so that's out of 3. Okay, all right, this next one, we want to find out when the second derivative, when the function is concave down. Okay. All right. So we want to find out when the function is concave down. So we know that's when the double derivative is less than 0. All right. Then f of x is concave down. Well, this is just some thought process. We have the derivative right here. We know if we take the derivative of this, we get the second derivative. Well, we know the derivative of this is just the values of the slope of the graph. Okay? So just thinking of the derivative in terms of the values of the slope of the graph, okay, we can solve this problem. Okay, so the slope of the derivative f prime of x determine the sine of f double prime of x. So on -3 to 2, f double prime of x is negative. 6 to 10, f double prime of x is negative. Therefore, on those intervals, f of x is concave down. You get a point for each interval, and you get a point for stating that the double derivative is negative. Really, you have to say because f prime of x is decreasing. Well, I'm not really sure that you have to say that, but you have to explain why you think the double derivative is negative. I'll go ahead and I'll leave that up to you to decide. Let's just say that if you said the double derivative was negative, you get a point. If you did that, even better. So that's out of 3. Okay. So, let's see. We're not adding up to 9 right here. Normally we add up to 9. Okay. Well, this one will just add up to 8. That's fine. Okay. So this problem adds up to 8. Go ahead and grade yourself, and we'll move on to the next one. So here are number 4. Okay, here's the information that I'm just writing down prior to solving the problem. Something's initially at rest. The acceleration due to time is 12t minus 4. The velocity is 0 at 0. And the position at 1 is 3. Okay, so when is it at rest? It's when the velocity, just when v of t equals 0, right? When the velocity equals 0. So we have to find when the velocity is 0. So first we have to find the velocity. Alright, so we have to integrate the acceleration. The integral of acceleration, that's worth a point. Okay, just getting the integral of that. And having your constant there too. Proper integration, don't be distasteful. Now plugging in your initial condition. Okay, that's a point. Alright, so getting C is 0, plugging in your initial condition. So getting the real formula is worth a point basically. Alright, let's go ahead and give yourself a point if you set the velocity equal to 0, and a point if you got both answers. So this will be out of 4. Okay. And then no JYA in this case, probably because it's a very long drawn out. They don't want to give any more points out. Alright, so now we need to find out what the position is. So we integrate the velocity. So the integral of velocity, if you got that, that's a point. If you plugged in your initial condition and got, if you plugged in your initial condition and got 4, that's a point. And here's your position formula. That's a point. So this is out of 3. Go ahead and grade yourself. Positive necessary. And if you did this wrong, but you wrote it out, and remember, one step behind wrong does not equate to the next step being wrong. Okay. So letter C. Find the total distance traveled. You could use the integral of velocity, which gives you the position, or just use the position. Okay. You know at time equals 1, it's at rest. We already found that. It's at rest. So we know when we find total distance traveled, we have to take into account that it may have traveled one direction, rested, and then another direction. So that's why when we if we're going to do the integral, we have to take into account the intervals 0 to 1 and 1 to 2. And same with the position. So no points awarded yet. Okay, what did we do? 4, then 3. We only have 2 more points. I guess we can make this a 3-pointer. Alright, so we want to find the position from 0 to 1. You could use the integral of velocity from 0 to 1. That's the alternate way. But when you work it out, you get -1 unit 1 unit traveled. Okay, that's a point. Finding the position from 1 to 2, taking the position at 2, subtracting the position at 1 here, you get 9 units traveled, so that's a point. And the total distance, knowing that we don't subtract these, total distance we're talking about, we're making all our distances the absolute values, so, or just 10 units, that's a point. So this one's actually, go ahead and grade it, pause it if you have to. This one's out of 10 points. Big question. Okay, there we go. Alright, so next, this one was fun. We had this thing going on here, the acceleration. Now first we were asked, is the velocity increasing? Well, we know if the acceleration is greater than 0, if the acceleration is greater than 0, then the velocity is increasing. Think about it. We have the acceleration, which is the derivative, the slope of the velocity. So if the acceleration is positive, that means the velocity is sloping up. Okay? So here's where the acceleration is positive, which means here's where the velocity is sloping up. Here's where the velocity is increasing, sloping up. So the velocity is going to have some sort of increasing slope right there, and some sort of increasing slope right there, and here it'll be decreasing. Okay? Alright, so basically, I think this was a JYA, so we'll give 1 point for your intervals, 1 point for your intervals, okay, and 1 point for stating that you have to state that the acceleration is the value of the acceleration is greater than 0. Okay, so just 1 point for your intervals, 1 point for your JYA out of 2. Okay, I mean, kind of want to double check on that, but I'm pretty sure you had a JYA on this one. Let's scratch that. I don't want y'all to take away points. Okay, let's just make each of these worth a point. Alright, so now we're being asked for the velocity. When does it equal 55 again? Well, it starts at 55, and we know the integral of the acceleration is the velocity, so the velocity is basically the area under the curve, and it starts at 55. Well, if we take the area under the curve and where are we at? And add it to 55, we can find the velocity at 6. Okay, so we take all this area and we're going to add it to 55. Okay, and so we get 115 feet per second. So we just do area is just base times height, 1/2 base times height. Okay. Alright, so, but the thing is, you're trying to, okay, well, we need to consider, you know, where else it could be 55. So, well, it's definitely not 55 right here. So let's consider, basically what you need to know that, that this area we added a certain amount of this certain area. Well, when we subtract that area, right, it's going to be 55 again. So right here at t equals 12, excuse me, alright, I need to scroll up. Okay. So right here we added that, got 115. Then we minused it at v of 12. So we minus the same area. V of 12 is 55. Okay. So basically at t equals 12, velocity equals 55 feet per second. That's basically it. This is kind of like just it's a 2-point question, I guess. If you show that you're adding and subtracting areas, show that you're, I kind of didn't do it here, shame on me, but show that you're adding and subtracting areas. I kind of just wrote the number because I knew it. But you have to show that you're adding each individual area, and we'll make this out of 2 for your answer, and showing that you added and subtracted area. There's the answer. Okay. Alright, C. At t equals 0, alright, what are we trying to find? We're trying to find the absolute maximum velocity. So we have to remember the extreme value theorem. Okay, we have to remember that it can occur at endpoints and critical points. Well, we have 2 critical points, and I know it's decreasing here, so that one really doesn't matter, but we're going to test it anyway. We'll cover all our bases. What's the velocity at 0? 55. Add the area to get this. It's minus the area to get that, add the area to get that. So we need to test it at the critical points and the endpoints in order to satisfy the extreme value theorem and find the maximum, the absolute maximum. So right here, at t equals 0, vt equals 55. I already found this one. At t equals 16, the velocity is less because the area is negative. So I minus that area. I already found the area at t equals 12, so I just basically took t equals 12 and minus the rest of the area, yeah, and I got 10 feet per second. And t equals 18, the velocity, we add the area again, so it's obviously this one, but we have to state the extreme value theorem, because the extreme value theorem is like our backbone, and like it's like what allows us to say that's the maximum, right? So you get a point for evaluating all four, 0, 6, 16, and 18. Okay, so you have to, I'm sorry, but you have to evaluate all four, guys. And then, I believe, in the case that you have to use the extreme value theorem, you have to state the extreme value theorem's hypothesis that, or the extreme value theorem that absolute maximum or minimum points can occur only at critical points or at endpoints. By testing each, I've been concluded that the time is t equals 6 and the absolute max velocity is 115 feet per second. So just state something about the extreme value theorem. It's all about testing your critical points and your endpoints. Okay, so that's actually a point. And if you didn't do that, I'm sorry. It's probably my fault. Okay, but we have to test it. We have to say something about the extreme value theorem. And I tell you what, I won't be mean. Not today. Okay, I'm not quite sure what the grading rubric says for this, but just know it's a good practice to state the extreme value theorem if you're using the extreme value theorem, which is testing critical points and endpoints to find a maxima or a minima. Okay, especially absolute. All right, I've concluded the time t equals 6 and the absolute max velocity is 115 feet per second. So there's a point and there's a point, which means, okay, we gave a point for testing those values down there. Oh, there it is. You can barely see it. 1 point, 2 points. This is out of 3 points. So you got to have this, and you got to have this, and you got to have tested your rest of your critical points and your endpoints. All right. Once again, we want to find an absolute min. So this is another EVT question. So the absolute min can occur at the critical points and the endpoints. By testing all the critical points and endpoints, endpoints of, endpoints of the absolute min of the velocity. Alright, let me start over. By the extreme value theorem, the absolute minimum of the velocity can occur at the critical points or endpoints. By testing all critical points and endpoints, I've concluded that the absolute min occurs at t equals 16. The velocity, b of 16, equals 10 feet per second. Since 0 is less than 10, v of t never reaches 0. So basically, they wanted to know if the velocity hit 0. Well, if I found the minimum, this is a little bit of a, you kind of have to know what to do. If you find the absolute minimum and it's not less than 0, that means everything's bigger than 0. Alright? V of t never reaches 0. Or you could say V of t is always greater than or equal to 0. Alright? Because okay, so basically right here you would have to have gotten that the absolute min, stating something about what you know about the absolute minimum. Alright, this in particular, the minimum value is 10. You could have just said that, I guess you could have said the minimum value is 10. And once again, if you're going to say that, you have to say something about the extreme value theorem. I'm not going to count it against you, but you know, that's something that's important. Alright, so 1 point for stating that the minimum was 10. 1 point for stating that v of t never reaches 0. This is out of 2. Okay? So 3, 2. Alright? 2, 2. So what was that? 3, 2, 6. This is out of 9. Okay? Alright, so last one, I think. Yep, last one. This was a doozy. I'm sure some of y'all are saying, well, I thought differential equations were easy. This one was not. Well, it wasn't. This was a tough one. Even I struggled for a minute or two on this one. Slope field was easy. Give yourself 2 points. Remember, the slopes have to be, since this is 0.5 and this is 1.5, this has to be significantly steeper than this. And these have to be positive. negative, 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 net positive, and 0. If you did that, then you were fine. Alright, here's my table to find my slope. Now, how do I find the second derivative? Well, I take the derivative of the first derivative, right? And that gives me the second derivative. Okay? So when I take the derivative of the first derivative, I get the second derivative. But I also end up with something interesting. I end up with 1/2 and y prime. Well, y prime is dy dx, so I have to substitute. I have to substitute my original dy dx in here. And I apologize for throwing this curveball at you, but hopefully some of y'all knocked it out of the park. We haven't done a second derivative in a while, implicitly anyway. Okay, so the question was, so you get a point for taking the derivative here, in my opinion. Well, actually, no, scratch that. You get a point for taking the derivative and getting the right solution. Now you get a point as well for knowing that the second derivative has to be greater than 0 in order, Alright, here we go. In order for it to be concave up. Okay? So I'll give you a point there. Now, this is tough. I don't think we've ever done this type of problem, but this is just something it's just a tough cookie right here. Okay? Since you have an equation stating what you know about the second derivative being greater than 0, make it a linear function, okay? And you could have stopped right here and said all solutions that satisfy this inequality. But I don't think that would be very appropriate. I would find a linear equation for it and then state that all solution curves are concave up above this line, because that would satisfy this equation, because you know how to do linear inequalities. Okay, your y-intercept is 1/2, down 1/2, you got your line, but it should be dashed, so a dashed line. Okay, you got a dashed line and you're shading above it. Sorry, I know that's pretty sloppy. Okay, but anyway, yep, y'all get the idea here. But anyway, I think it would have been okay for you just to say all x and y values will satisfy this inequality, but really it would have been nice to do it this way. All solution curves are concave up above this line, because that would make it greater than that. So either way, however you verbalize your second derivative being, you're going to have to give yourself some slack if you never got to this part, I guess. But that's out of 3. Alright? So we got out of 2, out of 3. Let's move on to the next one. Alright? This next one, okay, actually this whole problem was kind of a nightmare. Alright, so relative max means f prime of x, in this case dy dx, goes from positive to 0 to negative. Well, and we were supposed to find out whether it has a relative max, min, or neither. What I did, at first, I looked at the graph, and I said, oh, well, if I look at that point, the solution curve at that point has to follow these guidelines, and these guidelines state that the slope is going to be negative, 0, then positive. So I knew it was a relative minimum right off the bat. So in some cases, I guess AP readers may or may not like that. But I stated that by the graph, the derivative or the slope field shows that the solution curve decreases, stops, and increases. Therefore, there is a relative min at x equals 0, y equals 1. But thinking further, if I use the second derivative and I plug in those numbers, okay, that meant a solution's concave up, which meant it's a relative min. This is the this is simply stated the second derivative test, and we don't use it enough, plugging in numbers into the second derivative to justify a relative min. You can do that though. It doesn't happen all the time, doesn't happen a lot, but you can do it. But you would also have to state that the derivative equals 0 at that point as well, which it does. It does. You plug in x and y, x equals 0, y equals 1. So here, the double derivative is greater than 0, so it's concave up, therefore it's a relative min. I looked at the graph, said it's a relative min. Let's say you get out of 2, okay? 1 for stating that it's a relative min, 1 for how you got there. And right now I'm not quite sure what the AP readers want for how you got there. So how you got there, I guess it'd just be liberal in that case. So you could look at the graph, look at the second derivative, either or. Alright, so letter D kind of really ticked me off. Okay, I'm going to be quite frank, and I actually looked online to see how other people solved it, and I didn't like the way they solved it. Ugh, I didn't like it. So they use some fancy stuff, fancier than I know. But here's how. First I said, all right, y equals mx plus b. Oh my goodness. Then the slope of this solution line, well, the slope is the derivative, so I set it equal to the derivative. All right. So I said the slope is equal to the derivative. I'm going to get the slope somehow using the derivative. Well, then I ended up with this, which didn't make me happy. Okay. So then I said, all right, well, if I'm taking the derivative of this, I'm going to get m constant slope. Well, then the double derivative is 0. So I said, all right, where can I what formula can I concoct based on knowing the double derivative is 0? Well, if the double derivative is 0, then the double derivative, which we know, we've already found it in the previous section, is this. I set this equal to 0 and I get this. Well, that is a y and that is an x, thus it can count as a solution curve. It really can. Okay? It's a solution curve which all second derivative outputs are 0. Therefore, the first derivative is a constant, and the solution is a linear function. I know. Y'all are probably mad at me for giving you a hard differential equation. I'm sorry, but I figured I'd up the ante a little bit. I didn't know it was this difficult. So this one's let's see what this one is. Let's wow. I'm going to give you out of 2, okay? This was just a really tough one. I'm going to give you a point for the solution and a point for how you got there. And if you got there, awesome. If you didn't, then you didn't. But I would also give you a point if you use solution process, setting the slope of the linear function equal to the derivative, or if at any point you set the zero double derivative equal to the double derivative, I'd give you a point for that too. So that's where your points could come from. Just any trial and error process into solving this problem based on good functional calculus. All right, guys. So let's tally it up. 2 for this question. Oh, yeah. This last part. Line at which the concavity is 0. This line. Therefore, it is the only linear solution curve. And that is true. It is the only linear solution curve. And I guess that's kind of an oxymoron, linear curve. Alright, let's tally it. 2, 2, 3, and 2. So that would be 9. Out of 9, guys. That was a tough one. I've only seen really this is the first DiffyQ that I've seen that's just really tough. So hopefully you got something out of this. Your grades probably aren't going to be as good as it was a regular differential equation. I apologize for that. And have all this, if you can turn this into me before Wednesday or just throughout the week, come show it to me so I can help you with it. That'd be great. Thanks, guys. Peace out.